Thank you everyone for coming, and sorry for being a little bit late. So my name is Martijn. I'm from Eindhoven University of Technology from the Netherlands. And so this is joint work together with my supervisors, Nelly Litvak and Remco van der Hofstad. So today we are going to talk about community detection. So many networks like this one, you can identify groups of nodes that are better connected internally than the remainder of the network. So in network science, these groups of nodes are often called communities. And community detection is the task of partitioning a network into such groups of nodes. And so here, the network that we have over here is every node represents an American football team, and the link represents that these teams played against each other. And then the communities or the groups that you see here are then conferences, which is like a pool, like of the earlier stage of the tournament. So an overview of what we're going to discuss today. So I'm going to introduce a very general framework of community detection that generalizes several popular community detection methods, among which modularity maximization and Markov stability and some likelihood methods. So this framework has some built-in hyperspherical geometry. So what we do is we represent each of the possible partitions as a point in a hyperspherical geometry. And then we map the network as a whole to another point on that same hypersphere. And then to detect the communities in this network, we just find the partition that is closest to the point that we mapped our network to. So a few disclaimers to avoid confusion. So we're doing things with geometry, but we're not considering a geometry of nodes. We're not embedding nodes in some geometry. But instead, we take the whole graph and map it to a single point in this geometry. And so this geometry that we consider, it is also completely unrelated to any geometry that the network itself might have. So in some networks, like the nodes can also be have a natural position in space. Like for example, if you have airports and then they're connected to each other. But this geometry is unrelated to the geometry that we'll be discussing today. So first some introduction. So modularity maximization is one of the most popular community detection methods. So modularity measures is the fraction of edges inside communities minus the expected fraction according to some null model. So then what you do, you simply take the sum over all the node pairs that are of the same community. So then here this intra C represents the set of node pairs that are all in the same community. And then you count one if the node pair is connected. And then for each of these node pairs, you subtract the expected edge indicator there minus some constant gamma. So this gamma is a resolution parameter. If you choose larger values of gamma, then maximizing this will result into smaller communities. And if you use small values of gamma, then you'll detect larger and fewer communities. And so there's different null models that determine this expectation over here. So the one that's most widely used is the configuration model, or more precisely the Chong-Lu model. So here you correct for the degrees of the vertices. And then another more simpler null model is the Erdős-Rényi null model, where you assume that every node pair is equally likely to be connected. So this is modularity, and one of the most standard approaches to detecting communities is to simply take this function and maximize it over all the clustering C. So maximizing it over all the partitions of the nodes. So the way that this maximization is often done is by the Louvain algorithm. So this is nothing more than just a greedy optimization of partitions. So initially it assigns every vertex to its own community of size 1. And then it, in the first step, it iterates over all the nodes and tries to increase modularity by relabeling it to the communities of its neighbors. And then when that is no longer possible, when it has reached a local optimum of that, what it then does is it aggregates each of these communities and then repeats the same, but then with these aggregation nodes and relabeling them. So I don't think anyone actually proved it, and I also don't think that that it is easy to prove, but empirically they say that it runs in roughly linear time for sparse graphs, but I would very well imagine that it should be easy to come up with examples where it runs in more than where it runs slower than in linear time. So I have some animation here of this Louvain algorithm, but I think I would have to reshare my screen for it, because I don't think you can see this in Zoom.
No, we cannot see it for time being.
Yeah. Oh wait, new share. Can't I share the screen instead of? Yeah, okay, I'll just do this. Can you now see it?
Yes, now we can see it.
Now they can see it. Wait. Okay, and now you cannot see it again.
Yes.
Oh, wait, I think I have a better solution. Duplicate. Yeah. Now everyone can see it again?
Yes.
Yeah. Okay, so we have this animation here. So we have this this network. And then we start at a node and we try to relabel it to any of its neighbors. So the gray nodes indicate that they're assigned to a community of size 1. And so we just go over all these nodes. And as you see, sometimes it occurs that a node is labeled to the wrong community because these two pink ones shouldn't be together. But then in a later step, that will be fixed. So then we just keep going. And then at some point, like we revisit a few nodes. And then at this point, we obtain some local optimum. So we cannot improve modularity by relabeling anymore. So what we then do is we do this aggregation and we try to increase modularity by moving these things as a whole. So that means here that we merge these two communities over here. And then in the final step, we do this last merge. And then here in this case, it very nicely results in the global optimum. How do I? Yeah. Okay. Yeah. So that is how this Louvain algorithm works. So then an advantage of this Louvain algorithm is that it's very easy to modify this to optimize any other function over the set of partitions. And now what we are going to prove is that maximizing this modularity is actually the same as minimizing a distance between the graph and a partition. So the way that we do it is, so here we write again the definition of modularity, and then here we rewrite it. So here, these three lines, this equivalence sign means that optimizing the left-hand side over clusterings is equivalent to optimizing the right-hand side. So what we do here is we multiply by 2, which does not depend on C, so it does not affect the optimization. And then what we do then, we subtract this whole sum, and here again we see C does not occur there. So it is does not affect the optimization. And if we rewrite this, then so this is the sum over all the vertex node pairs. So then each of these intra community pairs occurs at least occurs once in the sum. So then we cancel this one out once. And then what we are left with is all the node pairs that are not intra-community pairs. So these are inter-community pairs. So nodes of different communities. And then these two sums we can nicely rewrite as this inner product. So where this Qij is just whatever we have over here in the sum. And this BC is this vector which is 1 for every intra-community pair and -1 for every inter-community pair. So that way we can rewrite modularity as this inner product. But so notice that the way that we map these clusterings to these vectors, that all of these vectors have the same Euclidean length. So they kind of lie on a hypersphere of this diameter, square root of n choose 2. So therefore, it is natural to look at the angular distance in this setup because they all have equal length. And so then if we rewrite this inner product in terms of this angle, then we get this. And so this Q over here, the length of that Q vector does not depend on C. The length of this BC is the same for every clustering. So then maximizing modularity is thus equivalent to maximizing the cosine of this angle, which is therefore equivalent to minimizing this angle. So we have seen that modularity maximization is equivalent to minimizing this angle between this point where we map our graph to and a clustering vector. And then there's also this other community detection method. It's called Markov stability. And we show that it also fits this framework. So you map the graph to some point, and then you minimize the angular distance to a clustering vector. So the way that Markov stability is defined is you have a random walk on a network. So the random walk is defined by this transition matrix. And we take its stationary distribution. We assume that the stationary distribution is unique. And then we represent a clustering as an indicator matrix. So that means that you have like, if you have k clusters, then you have n by k, and you have ones if node I is in cluster A and 0 otherwise. So the way that Markov stability is defined is as follows. It's this formula. I'm going to quickly dissect it. So what we want to know is if we look at a random walker that's just drawn from this from the stationary distribution. So its initial position is from this stationary distribution, and then we check in what community is it at this initial point, and then we wait for t time steps, and then we check again in what community is a random walker. So if the network has very strong community structure, then it's more likely to stay inside the same community. And so that is kind of what this first term measures over here. This diagonal of the stationary distribution times transition matrix to the power t. The entry ij is merely the probability that you started in state I and ended in state j. And then by multiplying it by these indicator matrices, you're simply taking the sum within each community. And then this over here is a correction term. So so this represents if you would have a random walker and you see what community it is, and then you take a different independent random walker and you see what community it is there. And then you compare the probability that they are in the same community. So this is kind of a correction term. And of course, if we wouldn't have this, then the optimum would always be to just have one community containing all vertices. But so what we're gonna show here is that maximizing this is again equivalent to minimizing this angle. And we're gonna prove something more general. So for any matrix X, and maximizing this trace thing is exactly equivalent to maximizing this cosine of this angle. So the way that we prove it is we simply we just write this trace as the sum. So the trace is the sum of all the diagonal entries over here. And then we just compute these diagonal entries by doing this double sum over here. And so then you get here xij, but it's multiplied with these entries of the indicator matrix. And the product of these indicator matrices is only one if they are both in the same community. So this is 0 if I and j are in different communities. So what we are left with is only the contributions of the terms that are in different communities. So, but of course we also get xii over there in this sum, and we get xji over here in this sum. But then we can do the same trick as we did previously. We just subtract this constant over here, which does not depend on C. And then again, we can rewrite it as this inner product, which we again can rewrite as this cosine. So this tells us that also maximizing Markov stability can be seen as just minimizing an angle between some vertex that you map the graph to and a partition. So now we have rewritten everything in hyperspherical geometry, but you might be asking, isn't it easier to think of Euclidean geometry because that is less curved and curves are difficult? So we could also rewrite this in Euclidean geometry, and maximizing modularity or Markov stability is also equivalent to minimizing the Euclidean distance. So you can see that as follows. So minimizing the Euclidean distance is equivalent to minimizing the squared Euclidean distance. And then we can rewrite it in this way. And then this q squared and the bc squared does not depend on c because this length of bc is constant. And then, so what we're left with is just minus this cosine, and maximizing that, minimizing that is equivalent to minimizing the angle. But the reason that we are working in hyperspherical geometry instead of Euclidean geometry is that in Euclidean geometry you have the length of the vector, which does not affect the optimization over clusterings at all. So kind of the length of this vector q is completely meaningless. And if we take the Euclidean space modulo the length of each vector, then what you get is automatically a hyperspherical geometry. And so that's the reason that we consider hyperspherical geometry. Now I'm gonna briefly explain some hyperspherical geometry that we will be using to explain this, to understand this framework better. So we have seen the angular distance is this inner product, but then normalized. And so when we define clusterings as these binary vectors, then there's 2 points that are special. So the first one, if you have the partition where all the nodes are in the same cluster, so it's a clustering consisting of one set, then its corresponding vector is simply the all one vector. And opposite, if instead we have the partition where every node is assigned to a community of size 1, then we have a -1 vector, because then each of the entries are -1. And these two are opposite poles in our hypersphere. And they have a special meaning in this geometry. And so we define the latitude. So yeah, it's just inspired from the definition in geography. Like we define the latitude as the angle between a vector and this -1 pole.
Martijn, can you just recall the definition of T of one clustering?
Yeah. But
so it's a vector of dimension n times n.
n choose 2. So
yeah, n choose 2. Okay.
Yeah, I think I could go back to this definition. Or I could.
In particular, I don't remember why the norm is the same for any clustering.
So it's not on this one.
Yeah, so you have B, C. This 1 if IJ, so BCIJ is 1 if it is an intrapair.
Okay, and -1 otherwise.
Yep. And so that is why the norm of this vector is always the square root of n choose 2. And so yeah, for this, that's why for these two partitions you get the all 1 and all -1.
Yes.
So we define this this latitude as the angular distance towards this -1 pole. And in particular, if we measure the latitude of a clustering vector, then this is simply given by this r cosine of this of 1 minus twice the fraction of node pairs that are intra-cluster pairs. And so if you have a partition, then the fraction of node pairs that are inside the same set can be seen as a measure of granularity. So in this framework, we will use the latitude of a clustering vector as a measure of the granularity of that cluster. So when you have a clustering consisting of a lot of small sets, then it will have a low latitude as it's close to this -1 pole. And if you have a clustering consisting of a few very large sets, then you have a large latitude because it's closer to this 1 pole.
But most of the partitions are in the south.
Yes, yeah, indeed. So almost all of them are in the southern hemisphere. Yeah. And so again, staying in this analogy with geography, we can define parallels and meridians. So parallels are these lines on the map, and meridians are these lines. And so in our setting, a parallel is the subspace of constant latitude. So just all vectors that have a certain value of the latitude. So yeah, here it is like a one-dimensional line on the map, but in our case it's n choose 2 minus 2-dimensional. So high dimensionality makes things a bit more difficult. So indeed we have the equator, which is the parallel with latitude pi/2, and most of the clusterings are below this equator. And if you have a vector anywhere on the hypersphere, then you can map it to a parallel of some latitude. So that's just taking the vector and moving it to the closest point on this parallel. And there's this formula for it. So the exact form is not so important, but what's important to see here is that it's a linear combination of the vector itself and the all-1 vector, and that these coefficients are just like can be computed easily. And similarly, a meridian is like one of these vertical lines on the map. So that is a geodesic between the two poles. And so for every vector on the hypersphere that's not equal to one of those poles, there's a unique meridian running through it. And this meridian can be parameterized by this parallel projection. So you just take the parallel projection for all different values of lambda. So, and then now we go into one more definition of hyperspherical geometry before we will actually explain why it makes sense to look at all these things. So, yeah, we have a hypersphere, and you can also look at angles on the surface of the hypersphere. So if you have 3 points on this hypersphere, you can make like the line from x to y and y to z. What angle do they make at y on the surface of the hypersphere? And in particular, if you have 2 meridians, then you might be interested in knowing the angle that they make at this -1 pole when they meet. So there's this nice formula for this angle. So yeah, the way that this angle is defined, by the way, is if you take if you want to measure between x -1 and z, then you project x and z to the tangent plane of -1, and then you simply take the angle in that tangent plane. And so if you would do this by hand, then you would find this formula over here, which is a function of the angular distance between x and y and of the latitudes of x and y. So the reason that I introduced this meridian angle is that if you take the cosine of this angle, then it turns out to be exactly equal to the Pearson correlation between 2 vectors. So yeah, if you have 2 vectors on our hypersphere, and then take the angle that the meridians make at this -1 pole, take cosine of that, that turns out to be exactly the Pearson correlation, which is kind of cool. And so if you do that for 2 clustering vectors, then like this Pearson correlation between these clustering vectors is a useful measure of how similar these clusterings are. So in some prior work, we compared a bunch of these similarity measures between partitions, and like looked into theoretical properties of these. And so many of these indices, like the Jacquard and the Rand index, they have like a bias that if you measure similarity, then it is more likely to attribute higher similarity values to clusterings that are either very fine-grained or coarse-grained. And so the clustering coefficient is one of the nice similarity measures that does not have this bias. So yeah, that's gives a nice interpretation of this thing. So if you have 2 clustering vectors, then this angle that the meridian makes is like a dissimilarity measure of how similar they are. And so similarly, yeah, we can. So that is why we call this angle that the meridians make the correlation distance between these 2 vectors. And so we will use this correlation coefficient or correlation distance as similarity measures between partitions over here. So just a short recap of what we have.
Can you back?
Yeah.
So if I understand correctly, the correlation distance is somehow a measure of the similarity that is orthogonal to the modularity of this partition. Am I correct in that description?
Yeah, so modularity is not the similarity between partitions.
Yeah,
so
yeah.
it's in a way it is so modularity is an angular distance, and you could think of this correlation distance as angular distance but then corrected for latitude.
Yeah, that's what I mean.
So yeah, indeed you could also detect communities by minimizing the correlation distance between this vector and this other thing. So that is possible to do, but weird stuff happens, so that's not what we're gonna do today.
Just what I meant, just to be sure that I understand, that correlation distance compares who the x tends to put with whom and who y tends to put with whom, independently of the modularity of these 2 clusterings.
Of the granularity of these clusters.
Oh, the granularity.
Yeah, so it corrects for that. So like another way to look at this correlation, at this meridian angle or correlation distance, is you project both of the vectors to the equator, and then you take the angle distance then. So just a short recap. So we are working in this hypersphere of in dimension n choose 2. This big N is n choose 2. And we index all vectors by node pairs or vertex pairs. We represent clusterings as binary vectors with a 1 if they're in the same cluster and -1 otherwise. We have this latitude, which is the angular distance to the -1 pole, and then we have the correlation coefficient, which is the Pearson correlation between these vectors, which has this nice geometric interpretations. And then the way that you can detect communities is by taking your graph and mapping it to this hypersphere, and then seeing which of the clustering vectors lies closest to this vector. So we define like a class of community detection methods as projection methods, if where we detect communities by first mapping the graph to this hypersphere and then minimizing this angular distance over the set of clusterings. And so we call the vector that we map the graph to, we call it the query vector, because kind of you're querying like which partition is closest to this vector. So you're searching for the like nearest neighbor of this Q. So we can do this minimization step, the projection, using the Louvain algorithm. So like this can be easily modified to minimize these distances. And so if we have a query vector, then we denote by L of Q just whatever clustering we get when we minimize this. So just a schematic overview, we have a graph, we map it to a query vector on a hypersphere, and then we minimize it and obtain a clustering vector which represents your partition. So there's many ways to do this step when you go from graph to query vector, and they all result in different community detection methods. So we've seen a few examples of ways to do this mapping. So when you want to do Markov stability, then that's equivalent to taking like a vector version of this matrix over here. And for modularity with the Gösgens null model, then you get a vector defined like this, with just adjacency minus the expectation. And for configuration model, you get a similar version, but then with this degree correction instead of these constant terms. But basically we can define this Q as a function of this graph in any way that we want. Like we can go crazy with it. So one particular thing that we can do is we can take linear combinations of these modularity vectors like this. No one's stopping us from doing that. And so these modularity vectors, they also have like a nice geometric interpretation. So like for each of these null models, you can choose the resolution parameter. And if you see at the query vectors corresponding that as a function of this resolution parameter gamma, then they correspond to straight lines on a hypersphere, like a geodesic. So for this Gösgens null model, so again we have that is like this. So then you have like a multiple of this all one vector that you're subtracting. So for this Gösgens null model, this line also corresponds to a meridian on a hypersphere. But for this configuration model, null model, it corresponds to a line that is not a meridian but crosses the equator at like an angle not equal to 90 degrees. But so we can also take linear combinations of these two vectors, and we can see what happens then, like how well is it able to detect communities. So here we did this for the Karate network. So this Karate network is this small network where you have a karate club, and then like social connections between these two, and then there's a conflict, and then the club splits up in two. And so if you look at configuration model modularity for different values of the resolution parameter, then you're on this line over here. And if you're at the Erdos range modularity, then you're on this line. But if you just go like slightly outside this line and take a linear combination, then you get like this thing which actually perfectly detects this this partition into two clubs. So of course this is very anecdotal evidence on like a very small network, but it shows at least that going outside this space of modularity vectors makes sense. And just some other ideas of like how you could choose this vector QA, is we could simply take the adjacency matrix and turn it into a vector. We could take, instead of like having an edge, we could count the number of common neighbors between each pair of vectors and use that as our and create a vector in that way. We could even consider the vertex neighborhoods of all the nodes and then take the Jacquard similarity between these two things. So then you get a vector where the entry ij tells you how similar are the neighborhoods of nodes I and j. But if you just take this and then feed it to Louvain and see what clustering you get, then you usually just get the clustering that puts everything into a single community, which is very unhelpful. So for example, if we simply take this edge vector, this adjacency matrix, then then all of the entries are 0 or 1. So there's never a reason to put two nodes apart. So what you will get is that the optimal partition in this way, in this for this EEG, will always be the partition into connected components of the graphs. And so if you do this, and if you do this for all the others, then you also usually just get like everything into a single community. So a way that we can easily fix this in our framework is to just simply add or subtract a constant times the all one vector to a vector. And so doing so is exactly equivalent to changing the latitude of our query vectors. So now a very general question that you could ask within this framework is like, given a vector, at what latitude should we put it so that we get a good community detection method? So yeah, we're given a vector and we want to decide the latitude so that the projection to that latitude works well in detecting communities. So in so the objective that we take here is we want to detect communities of the right granularity. So we want the latitude of this detected community to be similar to the latitude of the true community. So we're assuming that we have some generative model that generates graphs and community structure, and we want to decide which latitude should we choose so that the detected communities will be of the same granularity as the true communities. And so we came up with the following formula. It's a very general formula that seems to work in many ways, but it's a heuristic, so we don't have a full proof of why it works, but it seems to work often. So you have this formula, which is a function of the latitude of the ground truth clustering and a function of the meridian angle of this vector x that we're trying to project to a different latitude and the ground truth cluster. So so we get this formula. So I will explain a bit more about how we get this weird formula. But so first I will just show you that it works. So now with this heuristic, the setup that you have is you have a graph, then you extract some information of it. So this could be like the adjacency matrix, the number of common neighbors for every vertex pair, or just any other type of pairwise similarity measure between the nodes. And then we apply our heuristic to get a query vector, and then we use Louvain to detect communities. So first, to show that our thing actually works well. So if we take this Erdős range modularity, then if you take the standard value of the resolution parameter, so just take the resolution parameter equal to 1, then if many of the edges in the graph are between communities, so that means like if the graph is a bit noisy, then you very quickly see that the detected communities will have a much higher latitude than the true communities. But there's also a different way of choosing this resolution parameter, such that this maximization becomes equivalent to maximizing the likelihood of a blended partition model. And so that is also exactly the graph that we generate, that we apply this experiment on. So we take a blended partition model, generate a graph from that, and then we try modularity for 3 different values of the latitude. So here we see standard modularity. We see that it tends to result in clusterings that have much higher granularity, while we see that for this maximum likelihood method, it results in clusterings that are slightly lower granularity, like more fine-grained than the true clustering. And then this blue line over here is if we just apply our heuristic to this, and we see that stays close to 1, which means that the clusterings are of the same granularity. And then over here we measure like the performance in terms of this the dissimilarity between these 2 clusterings. So this is like the error of the community detection. We see that this green one, the standard modularity, performs quite poorly, and then we see that our heuristic and maximum likelihood perform roughly equivalent. So yeah, So do I have time to explain this heuristic in detail?
Maybe you have 10 minutes.
Okay. Yeah, then I'll just keep this a bit short. So the trick is, it turns out that whenever your query vector is at a position so that its angular distance to the ground truth is equal to this correlation distance, so that the angle between these meridians is equal to this angular distance, that then this latitude seems to work well, in that we get things of the right granularity. So then we made one observation that we based this on, and we have some tests showing that this works. But the way that we derive this is we want to solve for what latitude lambda does this hold. So does this angular distance equal this meridian angle? And so that is this. They can use some nice spherical geometry for this. Now we use the spherical version of the Pythagorean theorem, and then that way you get like this nice expression that we had over here, But so yeah, it's a heuristic, and we also don't entirely understand why it works so well, but it seems to work quite generally. So for many different types of graphs, and for many different types of ways in which you can map the graph to a query vector, this seems to perform well. So here we have several types of graph distributions. So here's the blended partition model, a blended partition model with different community sizes. And then there's the degree corrected partition model, where you have like more heterogeneity in the degree distribution. And at the bottom, that's this ABCD benchmark, which is a graph distribution benchmark, which has both power law community sizes and degree distribution. And so we see that here in most of these cases, like just applying or heuristic to any of these vectors works better than like this maximum likelihood approach. So especially here for the presented partition model, it's quite interesting that if you use the likelihood function of the model that you're working on, then it actually works worse than or with heuristic on simply the adjacency matrix. And even for like these other more realistic graph models, we see that our thing works significantly better than these other methods. So now, after all this high-dimensional hyperspherical geometry, you might wonder, like, isn't this super impractical to implement? But it's not that bad, actually, because what we're doing is only just applying the Louvain algorithm. Like this, all this hyperspherical stuff is just to get a nicer view of what we're actually doing. So this is the running times of my very suboptimal Python implementation of Louvain. But if we would do, like, if we would use a different implementation, like from some library that does the actual hard work in like C++, then these typically run like more than 1,000 times faster. But these have only been implemented for modularity maximization, so we cannot really use that. And then one other thing, so we now have like this very big space of community detection methods, which are represented by just the way in which you map your graph to a vector. And we can take linear combinations and we can do all kinds of crazy stuff. So what you could do is you could consider like some linear combination and just see which linear combination of these vectors results in the best community detection. So you could do that by just performing some grid search, which is what we're going to do. But we first make the problem a little bit easier. So first we have, because of the hyperspherical geometry, the length of this vector doesn't matter. So therefore we can fix one of the parameters. So we just say that the contribution of this edge vector over here will be 1. And then the next thing is that like just adding a constant of the all1 vector is just changing the latitude of this vector, but we have this nice heuristic to fix that value. So instead, we just do the grid search on 2 parameters. And here you see some results. So you have here the value of the coefficient of this of the Jaccard vectors. And here you have the value of the coefficient of this degree correction term. And we see that here, this is the one that obtains the highest score, and then see that it obtains like a ridiculously high score on the training set. So we use like 15 graphs to generate this figure on the left. And then we also generate 50 other graphs to actually validate how well it works. And so here we trained it on this ABCD graph generator, which is supposed to give graphs that are like realistic and that look like real world graphs. So we see here that we can use this whole framework to then optimize a community detection method for a specific graph generator. And so with that, I would like to thank you for your attention. Are there any questions?
Sorry, it's me again. Can you go back to the slide? They are saying that there are many possible choices for the query vector.
Yeah.
For
Yeah. Yeah. So for some reason, PowerPoint is very slow with when you include mathematics. Almost there.
Sometimes it's better to have the
Yeah, the PDF.
on the slide, then go directly to the slide. You should quit the.
Oh, yeah. Yeah.
I have the same problem with mathematics in
Yeah. Is it this one?
Yes. So just maybe more remarks than a question. In fact, I think it would be very natural to impose that the query vector that you choose will coincide with P of C in the particular case where your graph is a perfect clustering in the sense that it's a union of peaks. And in particular for the edge vector, it seems to me that it would be much more natural to consider the matrix instead of 0 and 1s having -1s and 1s.
Yeah. Yeah, so that is also what I did in like the earlier presentations and papers. But then like adjacency matrix, people usually talk about 0 and 1. But yeah, in our hypersphere, it also is kind of equivalent because they're on the same meridian. And then we're just gonna do this this heuristic, which is gonna say like where on this meridian do we need to be. So if we feed this vector over here to our heuristic, or if we feed the same vector but then with 1s and -1s, it gives the same vector after applying this heuristic.
Yeah, when it comes to using linear combinations, it's the same.
Yep.
If you do a vanilla version when you just use the edge vector, but in its -1,1 version,
yeah,
in some sense you have a canonical way to represent your graph in the hypersphere.
Yeah.
It's very tempting to use this query vector and see what happens. And does this one give nice results, or are there problems?
Yeah, so that is also what I like when I first thought of this whole hypersphere stuff. And this is like the most natural place to start, but it performs quite bad because like if you have a sparse graph, then you're usually connected to like a minority of your own community. So then it will almost always be more beneficial to not connect you to most of your community. So what you get is like just a very tiny sets that are like a refinement of the community or so. You just get like just very small dense communities that are way smaller than the communities that you're actually looking for.
Against that, you could look at the graph of the wolves of length, I don't know, 2, 3, something like that. So you see more of your community.
Yeah. Yeah, so this is similar to what this Markov stability does for this. If you increase the time scale over there, and then if you do that without applying on heuristic, then you do indeed see that you detect larger communities.
That would be a power of the matrix.
Yeah, the power of the matrix. So also this wedge vector over here, it's basically just a square, what we're looking at. So that is also a way in which you could get like larger communities. But yeah, then still you could take that vector and apply your heuristic, because also when you see this, when you use this Markov stability, you have this Markov time, and this kind of determines the size of the communities, the granularity. But it's just very difficult to see what scale should I have to detect the right scale.
The questions?
Yes. Maybe a simple question. When you do one way to handle granularity is to look at the hierarchical clustering. The small thing. Is there how does that work with this hyperspherical setting there?
Yeah, if you want to represent like a hierarchical clustering as a vector, that's a bit more tricky, because then you don't have like it's not binary. Are they in the same cluster? Are they not in the same cluster? But it's kind of how deep in the hierarchy are they connected?
But isn't it a kind of meridian, like kind of clustering? If you take the closest to a meridian partitions, don't you get the right kind of clustering in this person? Not exactly on the meridian, but,
yeah, you get often something like of a particular level of this hierarchical clustering, or with combination of different levels. So if you have something that has a hierarchical clustering, then you will typically get something that looks like this hierarchical clustering. But so if you want to sort of generalize this framework to hierarchical clustering, then I think you wouldn't get a sphere, because like the whole thing that we use here is that all of these things have the same length. So if you go to a different representation, then you get different properties and different geometry, which is cool.
The next level, so for this, I know that the Pascal will not be enough, but do you think this type of geometrical implementation could be extended to soft partitions? So you've got a certain number of labels, and each node has weight on each label.
Oh, yeah. Yeah, I think if you maybe impose some extra constraints so that they are still on like the hypersphere, then you could do it. But of course, you could still like figure a way out to map those labelings to a vector and still see whether whether minimizing a distance makes sense. But I didn't look into soft clustering. Any questions from the people online?
Okay, so let's thank the speaker again.